Grounding a generator involves several steps to ensure safety and proper operation. It's crucial to ground the generator, transfer switch, and main breaker panel to a common ground point. This is typically achieved by driving a ground rod and bonding all components to it. To ground the generator, firstly, install a copper-clad steel ground rod that is at least 6 feet long in the ground near the generator. Secondly, bond the generator to the rod. Connect the generator's grounding screw to the ground rod using a copper wire. The minimum size for this wire is 6 AWG. Thirdly, bond the transfer switch to the rod. Connect the transfer switch's bonding screw to the ground rod using a copper wire with a minimum size of 6 AWG. Fourthly, bond the main breaker panel to the rod. Connect the main breaker panel's grounding bus to the ground rod using a copper wire that is at least 6 AWG. Fifthly, bond the neutral bar to the ground rod, but only if it is not already in the panel. If the neutral bar in the main breaker panel is not bonded to the grounding bus, run a separate copper wire, a minimum of 6 AWG, from the neutral bar to the ground rod. Now let's discuss the neutral connections. The proper handling of the neutral conductor is just as important as grounding. First step involves bonding the neutral bar to the grounding bus in the main breaker panel. If the neutral bar is not already bonded to the grounding bus, run a copper wire, a minimum of 6 AWG, between the two. The second step is to ensure the generator isolates the neutral. Verify that the generator has an isolated neutral. This means that the neutral should not be bonded to the generator's frame or grounding system. The third step is to bond the transfer switch's neutral to the main breaker panel's neutral bar. Connect the transfer switch's neutral terminal to the neutral bar in the main breaker panel using a copper wire that is at least 6 AWG. When working with electrical systems, it's crucial to follow certain best practices. Firstly, use high-quality copper conductors for all grounding and neutral connections to ensure reliable conductivity and longevity. Secondly, ensure all connections are secure. Properly tighten all screws, bolts, and connectors to prevent loose connections that can cause resistance and heat. Thirdly, always follow the manufacturer's instructions for the specific generator, transfer switch, and panel being used. Manufacturers often provide detailed guidelines for grounding and neutral bonding specific to their products. Fourthly, if there is any uncertainty about any of the steps, consult with a qualified electrician. A licensed electrician can assess the specific installation, provide expert guidance, and ensure that all work complies with local electrical codes. Fifthly, after completing the grounding and neutral bonding, have the entire system inspected by a licensed electrician before connecting the generator to the electrical system. This inspection helps verify that all connections are correct, safe, and compliant with applicable regulations. Understanding the National Electrical Code, or NEC, is essential for safe and compliant electrical installations. Article 250 of the NEC covers grounding and bonding requirements. This section provides detailed information on how to properly ground electrical systems to ensure safety and minimize the risk of electrical shock. The NEC specifies the minimum size of grounding conductors based on the size of the overcurrent protection device in the circuit. For example, a 20 amp circuit typically requires a 12 AWG grounding conductor, while a 60 amp circuit requires a 10 AWG grounding conductor. The NEC requires that all metal enclosures containing electrical conductors be grounded to provide a path for fault current to return to the source. This helps prevent voltage from building up on the enclosure, which could create a shock hazard. Ground rods must be installed so that at least 8 feet of the rod is in contact with the soil. If the soil is rocky or unsuitable for driving a ground rod, it is permitted to bury the rod horizontally in a trench. The NEC requires that the neutral conductor be bonded to the grounding system at the service entrance. This ensures that there is a low impedance path for fault current to return to the source, which helps strip the overcurrent protection device and energize the circuit. When installing a generator, it is important to ensure that the neutral is either switched or isolated to prevent objectionable current from flowing through the grounding system. An ungrounded system is an electrical system that does not have a direct connection to ground. While these systems can offer some advantages, they also have significant safety concerns. In an ungrounded system, a single fault to ground will not trip the overcurrent protection device. This means that the equipment can continue to operate with the ground fault, which can create a shock hazard. Ungrounded systems are more susceptible to transient overvoltages, which can damage equipment. Because there is no direct connection to ground, voltage spikes can occur during switching operations or lightning strikes. These overvoltages can damage sensitive electronic equipment and reduce the lifespan of electrical components. Ungrounded systems can be difficult to troubleshoot because there is no reference point for measuring voltage. When a ground fault occurs, it can be challenging to locate the fault because the voltage on the system will shift, making it difficult to determine which circuit is affected. A separately derived system is an electrical system that receives its power from a source that is separate from the main electrical service. Generators, transformers, and UPS systems are examples of separately derived systems. When installing a separately derived system, it is important to follow specific grounding and bonding requirements to ensure safety and prevent ground loops. The neutral conductor of a separately derived system must be bonded to the grounding system at the source. This creates a low impedance path for fault current to return to the source, which helps trip the overcurrent protection device and energize the circuit. The equipment grounding conductor for a separately derived system must be sized according to the requirements of the NEC. This conductor provides a path for fault current to return to the source and helps prevent voltage from building up on equipment enclosures. When installing a transfer switch, it is important to ensure that the neutral is either switched or isolated to prevent objectionable current from flowing through the grounding system. This helps prevent ground loops and ensures that the grounding system functions properly. Ground loops can occur when there are multiple paths for ground current to flow. This can create circulating currents that can cause interference, noise, and even damage to equipment. To prevent ground loops, it is important to ensure that there is only one path for ground current to flow. This can be achieved by properly grounding and bonding all equipment and by using isolation transformers or other isolation devices. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges. These devices divert excess voltage to ground, which helps prevent damage to sensitive electronic equipment. SPD should be installed at the service entrance and at any downstream panel wards that serve critical equipment. SPD are rated by their surge current capacity, which is the amount of current that they can safely divert to ground. When selecting an SPD, it is important to choose one that is appropriately rated for the specific application. SPD should be installed in accordance with the manufacturer's instructions and the requirements of the NEC. The grounding electrode system is the network of grounding electrodes that are used to connect the electrical system to ground. This system typically includes ground rods, ground plates, and metal water pipes. The grounding electrode system must be installed in accordance with the requirements of the NEC. Ground rods must be installed so that at least 8 feet of the rod is in contact with the soil. Ground plates must be buried below the frost line. Metal water pipes can be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet. The grounding electrode conductor is the conductor that connects the grounding electrode system to the electrical system. This conductor must be sized according to the requirements of the NEC. The grounding electrode conductor must be made of copper or other approved material. The grounding electrode conductor must be protected from physical damage. Equipment grounding conductors provide a path for fault current to return to the source. These conductors must be sized according to the requirements of the NEC. Equipment grounding conductors must be made of copper or other approved material. Equipment grounding conductors must be securely connected to all metal enclosures and equipment. Bonding jumpers are used to connect metal enclosures and equipment together to create a continuous grounding path. Bonding jumpers must be sized according to the requirements of the NEC. Bonding jumpers must be made of copper or other approved material. Bonding jumpers must be securely connected to all metal enclosures and equipment. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect people from electrical shock. GFCIs monitor the current flowing in a circuit and trip the circuit if they detect a ground fault. GFCIs should be installed in all areas where there is a risk of electric shock, such as bathrooms, kitchens, and outdoor areas. GFCIs are available in several different types, including receptacle type, circuit breaker type, and portable type. Arc fault circuit interrupters, or SIs, are devices that are designed to protect against electrical fires. SIs monitor the current flowing in a circuit and trip the circuit if they detect an arc fault. SIs should be installed in all branch circuits that supply power to living areas. SIs are available in circuit breaker type and outlet branch circuit type. Regular inspections and maintenance are essential for ensuring the safety and reliability of the grounding system. Inspection should be performed at least annually by a qualified electrician. During an inspection, the electrician will check the grounding electrodes, grounding conductors, bonding jumpers, and ground fault circuit interrupters to ensure that they are in good condition and functioning properly. Any damaged or corroded component should be replaced immediately. The electrician will also test the ground fault circuit interrupters to ensure that they are tripping properly. Safety is paramount when working with electrical systems. Always to energize the circuit before working on it. Use appropriate personal protective equipment, such as gloves and safety glasses. Follow all applicable electrical codes and standards. If there are any uncertainties, consult with a qualified electrician. Proper grounding and neutral bonding are essential for ensuring the safety and reliability of electrical systems. By following the guidelines outlined in this discussion and consulting with a qualified electrician, one can ensure that electrical systems are properly grounded and bonded. This will help protect people from electrical shock and prevent damage to equipment. Generators play a crucial role in providing backup power during outages. Proper grounding and neutral connections are paramount for safe operation. If the generator is not properly grounded, it can pose a significant electrical hazard. Proper grounding ensures that the generator operates safely and efficiently. Regular inspections and maintenance are crucial to identify and address any potential issues before they escalate. This proactive approach helps maintain the generator's reliability and extends its lifespan. Investing in high-quality grounding materials is a prudent decision. Using durable copper conductors and secure connectors ensures long-lasting, reliable grounding.